Hello, I'm Porter. Today, our training topic is Otn protocols. With the rapid development of the IP-based networks, transport network evolved from the simple topology like the point-to-point and ring topologies to the mesh topology. And the transport and service networks are increasingly converged at network edges. And the vertical structure of networks tend to be flattened. So under this background, the traditional SDH plus WDM network has many disadvantages. So now the optical transport network, the OTN, stands out. As you can see here, after learning of this course, you'll be able to first understand the OTN layers, the frame structures, the maintenance signals, and functions of each layer, and then know about how to handle OTN electrical layer alarms and performance events. And finally, you should be able to analyze and locate the OTN electric layer faults of WDM products. And for this course, we totally have 6 chapters. For chapter 1, it was the OTN overview. Chapter 2, interface structures and multiplexing mapping principles. Chapter 3, frame structures and overheads. Chapter 4, trail layers and maintenance signals. Chapter 5, common alarms and performance events. Chapter 6, application of OTN overheads. So first, let's look at the OTN definition. So what is the OTN? So here we give you the definition. An optical network consists of optical NEs connected by optical fiber links. It enables transmission, multiplexing, routing, management, supervision, and protection of client services based on the optical channels. And here we show you one important feature of the OTN, that is client independence. That means the transmission settings of any digital client signals are independent of specific client features. So this is the OTN definition. Here we show you the OTN features, and we do the comparison between the OTN with the traditional SDH and the SoloNet first, and then we do the comparison between the OTN with the traditional WDM. So first, let's look at the OTN advantages compared with traditional SDH and SoloNet. So first, we can find the OTN have huge capacity and enough bandwidth. And then for the OTN, we can provide a lot of the high rate interface, like 100G, like 40G. And then it can provide maximum 6 levels for the nested or overlap TCM connection monitoring. And also it can support flexible network grooming and protection capabilities. For example, we can use the ROADM, and also we have the protection such as the old UK SNCP. And it will also have the powerful FEC functions that can guarantee the line transmission performance. Okay, another one is the comparison between the OTN with traditional WDM, and we also have the advantages. For example, we have enough the overheads for monitoring, so we have very powerful OEM and protection and network stability. And then we can provide the flexible optical layer and electrical grooming. Okay, and here you can find we have different OTN standards. For example, the first one was the device management. We called it G.874. Okay, and we have the jitter and performance, network protection, including the linear protection on an OTN network and ring protection. For the device functions and features, structure and mapping. So here, next we're to learn is for the mapping and multiplexing. So we will use the G.709, the interfaces on an OTN network. And also we have the standards for the physical layer features and also the architecture. If we use the ASUN, so we will use the standard that is G.8080. And for chapter 2, we'll explain to the interface structures and multiplexing mapping principles in the OTN. So for this page, it's very important to understand the OTN interface. So for the title, we call it OTM N.M. So later I'll explain to you what's the meaning for that. As you can see here, so first we have the client signals. For example, we have GE services. So it will ask the payload for the OPUK. And then we add the OPUK overhead. So this was the OPUK signal. For the OPUK signal, then we add the ODUK overhead. So this is the ODUK signals. And for the ODUK, it will have as the payload for the OTUK, and then we add the OTUK overhead. And also at the same time, we add the FEC overhead. So this is the OTUK signals. So finally, the OTUK signals will as the payload for the OCH. And for the OCH, it will also add the OCH overhead. So this is one optical channels, OCCP. And for multiple optical channels, we'll ask the payload for the OMS, because here we have the multiplexing unit. So this is the OMS payload. And there we will send the signals to the FIU, that is the OTS payload. And for here, we have another one for the OSC. So this one we call it OS. And for the OS, we also call it non-associated overhead. That is the common management overhead that we used for monitoring. So this is the relationships in the OTM N.M. So here I want to explain to you what's the meaning for this N. This N means the number of the wavelengths in the system. And this M means the rate for the wavelengths. If it is 1, that means the rate it was 2.5G. If it's 4, that means it was 100G. And for here, we show you another way. You can see this is different OCH. This is different OCH with different color because they have different frequency, 1 to N. And plus the OSC. So this is the signal for OTM N.M. Okay. And for another page, we show you the OTM NR.M. So compared with the previous one, from the client signal, OPUK, ODUK, OTUK, then go to the OCH, it's the same. So only the difference is just here. For the OTM NR.M, this R means reduced. So in this page, we don't have the OSC, so that is the difference. So here we mentioned no OSC is involved. So this is the OTM NR.M. And for here, pay attention, we have the OPUK signal, ODUK signal, OTUK signal, and we have different background color. So for the OPUK, ODUK, OTUK, they are electric layer signals. And for the OCH, for the OMS, and for the OTS, they are optical layer signals. Okay, so here we show you the architecture and interface of the OTN. And we have two different parts. For this one, from the OPUK, ODUK, OTUK, OCH, OMS, OTS. So this one we call the OTM N and .M. Another one, it's not including the OSC. So this is the NR.M, means reduced. And here we show you the meaning for different signals. For example, OPUK means optical channel payload unit key. This key can be different value. For example, can be 1, can be 2, 3, 4. Different numbers has different capacity. So here I have the ODUK, means optical channel data unit. OTUK, it was completely standardized optical channel transport unit key. And here we have another one, OTUK V. This means the functionally standardized optical channel transport unit key. And then we have the OCH. So here, what I said before, OPUK, ODUK, OTUK, they are electric layer signals. And for the OCH, OMS, OTS, or OPS, they are the optical layer signals. So for example, the OCH means optical channel with full functionality. So this is just one wavelength. If it's OCHR, means reduced. And for the OMS, it was the optical multiplex section. The OMS is between the OM and OD, means from the optical multiplexer to the optical demultiplexer. Between this part, we call it the OMS. And for the OTS, means optical transmission section between the two OA, we call it OTS, or between the two FIU, we call it the OTS. And for the OPS, this one was in the reduced OTM NR.M. We have the OPS, means optical physical section. And last one, OTM, optical transport model. So this was the architecture for the OTN. So let's see it again. So this part, like the IP, MPLS, ATM, Ethernet, STM, you can consider this was the client signals. So the client signals were as the payload for the OPUK. Then for the OPUK were as the payload for the ODUK. So for the ODUK, whereas the payload for the OTUK, we add the OTUK overhead and also we add the FEC. Then it becomes one optical channels. So multiple OCH will be multiplexed in the OMS. Then the OMS will be together with the OSC to the OTS. So this is the architecture and interfaces of the OTN. So next, we are to show you the optical layer multiplexing and mapping structure. As you can see here, we have two different parts. You can divide it like this: the upper one and the lower one. So we first analyze the lower one because here we have the OTM N.M. So this is what we used. So for example, first here we have the client signals. So we have client signals. The client signals will first go to the OPUK. And here we use the OPU1. That means this client signal, the red, that is 2.5G. So it has the OPU1. Then it will go to the ODU1. If the wavelength, if the OCH, the capacity, it was 2.5G. So we will choose mapping the ODU1 to the OTU1. Then this is one wavelength. If the line rate, it was 10G or 40G. So here we will do the multiplexing. For example, from one ODU1, we will use 4 ODU1 to do the multiplexing to one ODU2. From ODU1 to ODU3, we need how many? We need 16 ODU1. From ODU1 to ODU4, here we need 80. You can see 4 multiply 4 multiply 10. So that is 80. So here ODU1 to this one, ODU4, sorry, 40 here we should use. So here we can see we have OTU1, OTU2, OTU3, OTU4, even we have OTU5. So this is different OTUK. Then we add the OCH overhead. So this is different optical channels. So here we have 1, 2, 3, 4, 5. We have 5 channels. And for these 5 channels, it will working as the payload for the optical channel. Then the optical channels together with the OSC. So this will be the payload. We call it the OTM N.M. This N, the number will be 6 because here we have 5 optical channels with 1 OSC. And this M depends on the rate of this line card. So here I have the 1, 2, 3, 4, 5. So this M means 1, 2, 3, 4, 5. So the difference of the upper one is that here, for this one, we have the NR. So compared with the lower one, for this configuration, we don't have the OSC. but for other part, it's the same as the OTM n.m. Okay, and here we show you the ODUK multiplexing and the mapping structure. As you can see here, we use the ODU0, for example. We have the client signal, OPU0. So this client signal will be G. So we will go to the ODU0. So you can find from ODU0 to ODU1, we need 2 ODU0. From ODU0 to ODU2, we need multiplex 8 ODU0. From ODU0 to ODU3, so here we need 32 ODU0. From ODU0 to ODU4, so here we need 80. And from ODU0 to ODU5, we need 320. So why here we have these numbers? Because we know for the ODU0, the red, it was 1.25G. And for ODU1, the red, it was 2.5G. For ODU2, the red, it was 10G. ODU3, 40G. ODU4, 100G. ODU5, 400G. So this is why for 2 ODU0 multiplexing into 1 ODU1, 8 ODU0 multiplexing into 1 ODU2, 32 ODU0 multiplexing into 1 ODU3, and 80 ODU0 multiplexing into 1 ODU4. So another example we show you for the ODU1 to OTU1 we only need to add the OTU1 overhead and FEC. From ODU1 to ODU2, so here we need 4 ODU1 multiplexing into 1 ODU2, because for the ODU1, the red, it was 2.5G, and for ODU2, the red is 10G, so we need 4 ODU1. And from ODU1 to ODU3, we need 16. Okay, I think now you understand the mapping and multiplexing for the ODUK signals. So for example, I have one question. If I want to multiplexing the ODU2 to the ODU4, so how many ODU2 we need? So the answer will be 10, because ODU2, the capacity was 10G, and for ODU4, the capacity, it was 100G. Okay. And here we show you the ODUK, the TDM, time division multiplexing. We can multiplex from low order ODUK into the high order ODUK signals. So here you can see 2 ODU0 are multiplexed into 1 ODU1. 8 ODU0 or 4 ODU1 are multiplexed into 1 ODU2. For the ODU3, we can multiplex 32 ODU0, 16 ODU1, or 4 ODU2, or here 3 ODU2E. So here pay attention. The red for the ODU2 and ODU2E is a little bit different. So for 4 ODU2 can go to 1 ODU3, but if we use ODU2E, so for 1 ODU3, maximum can only support 3 ODU2E. And last one, we'll show you the ODU4, how many ODU0, ODU1, ODU2, or 2E we can support. And here pay attention, we also can support the mixed transmission. For example, we can multiplexing the ODU0, ODU1, ODU2, ODU3 at the same time to the ODU4. But just make sure the total bandwidth for the low order ODUK less than the bandwidth of the high order ODUK. It's okay. In this page, we have one example how to multiplex 4 ODU1 signal into 1 ODU2 signal. As you can see here, this is the frame structure for the ODUK. So this is the 1 ODU1, and for example, here I have client signals like STM16. So this service capacity was 2.5G. So it was the payload for the OPU1. So then we add the overhead, and also we add the ODU1 overhead. So this is the ODUK signal, and here we have the alignment signals. Okay, so we need to multiplex 4 ODU1 into 1 ODU2. So not like the SDH. For the Otn multiplexing, the frame size is fixed. The frame size is fixed. That means the frame size for the ODU1 is the same as the ODU2. No difference. But we know the audio2, the rate is 4 times of the audio1. So in the Otn multiplexing, we don't change the frame size for the O2K signals, but we change the frame speed. Okay, so after we got the audio2, then we add the O2K overhead. We add the O2K overhead here, O2 overhead. So this is one completely O2K frame, O2K frame. So here we have the O2 overhead, and finally here we have the FEC. So this is the completely O2K frame. And for this frame size, it was 4 rows and 4080 columns. And here we show you the frame rates for the different O2K signals. Normally we see for the O21, the capacity, it was 2.5G, O22, it was 10G, O23, 40G, O24, 100G, but that one is not accurate. So the accurate nominal rates we provided here. So for the O21, the rate, it was 266,057.143 kilobits per second. Okay, so you can calculate how many megabits or how many gigabits. So this is the frame rate for the O2K, and this is the formula how we do the calculation. And here we have the numbers like 255, 239. This means how many overheads in the O2K frame. Another one, we show you the frame period, or we call it the frame rate. As you can see, audio1 and audio2, their capacity is different, but their frame size is the same. So their frame period is different because the audio2, the capacity is 4 times of the audio1. So the transmission period of the audio2 is only 25% of the audio1. And here the unit is nanosecond. We know in the SDH, the frame size is flexible. STM1, STM4, the frame size is different, but their frame period is the same. All of them is 125 microseconds. But here, for the Otn signal frame period, is different for different signals. Okay, so now you understand why for the audio2, the capacity is 4 times of audio1 because its frame period is less than audio2. Okay.